this is definitely a skill you need to have, and we can tell by the title of this that these are the kind of problems that are on the AP exam.
Mm-hmm.
And I do have a number of AP exams. I have at least 2, I think 3 tests. And I can find more problems like this. Okay? Let's talk about this problem. What we're looking at here is the derivative of f. Okay? What they're going to ask you about are the original function, f, and the second derivative of f. So, these tend to be kind of difficult because it's difficult to think of in terms of a different kind of graph. Let's look at A. For -5 to 5, find all values of x where f has a relative maximum. Well, first of all, which points are we going to look at as possible contenders?
Would it be the x-intercepts?
Yeah, -5, -3, 1, and 4. Now, if I have a function like that, for something to be a relative maximum, the slopes have to go from plus, plus, plus to minus, minus, minus. If something is a relative minimum, they have to go minus, minus, minus to plus, plus, plus. Okay? So, let's use that test. First of all, at 5. Do we know what's happening to the right of 5? Are we increasing or decreasing? -5, excuse me. In other words, let's take each of these points left to right and see if we can figure out which ones might be relative maximums and which ones cannot be relative maximums.
Is it increasing after 5?
Yeah.
Or -5?
Yes. In other words, because this is positive between -5 and -3, that means the original function is increasing. Therefore, that point cannot be a relative maximum. Coming out of that point, we have positive slopes. It means that's not a relative maximum. So let's look at this second point. What's happening around that point? What are the slopes doing? In other words, if we apply the first derivative test to determine whether that could be a maximum, in other words, we don't know. That could be a maximum, that could be a minimum, it could be neither. What would make it a maximum?
It's going from negative to positive, or
the other way around.
Positive to negative?
Yeah. We need that to be happening. It's got to go from positive to 0 to negative. Well, that's exactly what's going on there. It's going from positive, and remember we're talking about the slopes on this graph. Always keep that in mind, that your first derivative is slope. So the slopes are going from positive to 0 to negative. That's a relative maximum.
Okay.
Okay. Now let's go look at this point. What are the slopes doing?
They're changing from negative to positive.
Which is this situation. That's a minimum. That is a relative minimum, not a maximum. Okay. And how about here? Oh, let's see. This one here.
Is there something wrong with the fact that it's just a straight line? Or
No, it's still going from positive slopes to negative slopes. Positive slopes to 0 to negative slopes. Okay? The fact that it's a straight line means that the second derivative is a constant. Right? In other words, we're always talking about slope. Never forget that. Okay? So the second derivative between there and there would represent the slope of that straight line. The second derivative from 1 to 2 would represent this slope here, which is clearly a slope of 2. So the second derivative, this is certainly going to be positive. Of course, we know that because it's increasing. And the second derivative is going to be negative here because it's decreasing that whole way. So always remember those underlying things. In other words, should I put my picture up again that shows function, first derivative, and second derivative? You just can't.
Sure.
You can't ignore all of those principles. In other words, those are the underlying principles of calculus, is the relationship between that first derivative, the function, and the second derivative. In other words, there's my picture. And the beauty of this picture is that they put all of them one below the other. So you can verify that when this is increasing, this is positive. When this is decreasing, this is negative. If I have a relative maximum, I know my slopes have to go from positive to negative, which it does. Inflection points, where the concavity changes, show up really clearly here. There's only one inflection point right there. Where does that occur? That occurs where the concavity goes from concave down to concave up, and it's right there, that middle point. And the second derivative is 0 right there.
Okay.
Okay. Let's look. So for answer A, the only two of the 4 zeros that satisfied our condition for a maximum where it has to go positive to negative slopes on either side of the 0 are -3 and 4. Part B. In that interval, find all values of x at which the graph of f has a point of inflection. Justify your answer. Well, what are our possibilities?
Would it be
where is the derivative? In other words, inflection. The moment you hear inflection, think second derivative. Okay?
So wherever that's equal to 0?
Yeah, where is the second derivative equal to 0 on this first derivative curve? Not just 0, but 0 or undefined.
I think -4.
Correct?
-1.
Correct?
And 2.
Correct. At least I think at 2. In other words, wherever our first derivative of this curve is equal to 0 or undefined represents a possible inflection point. So I do believe that it's -4, -1, and 2. And notice that the question says, what values of x? Oh, no, it didn't. I thought it said has a possible point of inflection. And it's saying for sure that it's a point of inflection. Let me think for a moment. Okay. I'm comfortable with the answer that's -4, -1, and 2. Remember that points of inflection come when concavity changes. So let's just examine each of these 3 points just for the heck of it. At -4, the slopes are all positive. So that means the original function is always increasing. The thing is, it can always be increasing like this. I didn't draw that quite the way I wanted to. Notice that there's concavity changing there. There definitely is a point of inflection somewhere about there where the concavity goes from concave down to concave up. And this is, what I've drawn here is the original function. This is f of x. Okay? So if I examine f prime of x here, is all I still see is plus, 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 plus. So points of inflection can definitely be surrounded by slopes being the same. Well, in this case, -4 is surrounded by positive slopes on either side. So -4 definitely looks like a point of inflection. -1 also. It's surrounded by negative slopes on either side. Well, I can just draw something that looks like that. Here's concave up, here's concave down, there's a point of inflection right there, and it's negative slope, negative slope, negative slope. So -1 almost certainly is an inflection point also. Now the one that is troublesome is 2. 2, 2. Is that necessarily a point of inflection? Well, we have slopes going from positive to positive, right? In other words, that's a positive slope. That's also a positive slope. Don't get confused. It looks negative, but that's the slope of the derivative, not the slope of the function. The original function is positive, increasing, and increasing here. And then it does something right there. Why would we cannot take the second derivative, so the second derivative doesn't exist because it's a cusp or a corner. I still think that's an inflection point. I'm trying to figure out what must our graph look like so that we would end up with the first derivative being a corner or a cusp. For the moment, let's go with those 3 points. There might be something about this point 2, 2 that I'm not considering. This is always where it gets difficult in calculus. Is not where your zeros lie, but where your first derivative doesn't exist lies.
Okay.
Here we have positive slopes, and then a point where the slopes instantly are still positive. something happens right there so that we can't differentiate. It's hard for me to work backwards on those kind of points. Always has been. Let's go on and maybe we'll answer it as we answer the rest of them.
Okay.
Find all intervals on which the graph of f is concave up and also has positive slope. Well, for it to be concave up, what does the second derivative have to be?
Positive?
Yeah, concave down means the second derivative has to be negative. So starting from the left, where is remember the second derivative is the first derivative of this function, right?
Mm-hmm.
So where is the second derivative positive, starting from right there? So where this function is what? Remember the relationship between function and first derivative. For first derivative to be positive, the original function has to be increasing. So I can say the second derivative, for it to be positive, the first derivative has to be increasing, right?
Okay, yep.
So from -5 to -4, we have an increasing first derivative. That means a positive second derivative.
So it's concave up.
Concave up from -5 to -4.
Okay.
We already figured there's an inflection point there, right? From the previous question. So we expect it to be concave down now. Well, the first derivative is decreasing from here all the way to there. First derivative is decreasing, second derivative is what?
Negative.
From -4 to -1, the second derivative is negative, therefore it is concave down.
Down. Yeah.
And that's an inflection point. And then we start increasing up again. So, in other words, the second derivative is going to be positive from -1 all the way up to that point there. Because this function, the first derivative, is increasing from -1 to 2. Therefore, the second derivative has to be positive. That means concave up again.
Okay.
Well, first derivative is decreasing from this point to that point. Second derivative's got to be negative. Concave down. So it looks like our answers to B probably were correct. We went from concave up, concave down, concave up, concave down. Should be 3 inflection points there. -4, -1, and 2. Now, the second part of that question, find all intervals of which f is concave up and also has a positive slope. Well, let's look at the f is concave up and has a positive slope. Well, where would that be on this graph? Starting from where we were defining our intervals, where it was concave up, we started at -5. We realized it was concave up from -5 to -4. But does that have a positive slope?
Yes.
Yeah, this is positive. Anything above the x-axis means it has a positive slope. Remember, this is the first derivative. And this is all about slopes. This is what the slopes are of the original function. So the answer to question C is each of our intervals that are above the x-axis. So it was concave down from here all the way to there, and then it was concave up from here to here, but doesn't have a positive slope there. It's still concave up from here to here and has a positive slope. And it's concave up from there to, no, hold on, excuse me. It's concave down. So our interval for the first part of C was from -1 to 2, but now we know for it to have a positive slope, it's only from 1 to 2. From 1 to 2, the second derivative is concave up because it's positive, and the first derivative, which is the slope, is positive. So our only two intervals for C, really, are from -5 to -4 and from 1 to 2.
Okay.
Now D, find the absolute minimum value of f of x over that interval. Explain your reasoning. The absolute minimum. Well, what do we need to do? We need to examine where the minimums are and the endpoints. I'm sure there's some reason they told us that f of 1 was equal to 3, but I haven't figured out what yet. Well, that's a potential. Let's see. The slopes went from negative to positive. That's a minimum right there. So that's one of our possible solutions. And they tell us what that is. F of 1 is 3. So we're going to be able to compare it with our other possible minimums.
Which is -5, right?
Well, hold on a moment. Let's see. Where did we... that's a possible minimum right there, yeah. -5. But we don't know what that value is. Let's ignore that one for a moment because I don't know what to do about it. Other possible minimums, not there because it's going from positive to negative. So that's a possible maximum. There's no way it could be an absolute minimum. This one here goes from negative to positive. So this could be a minimum. And they're telling us that it has a value of 3. And what were our other possible minimums? Slope had to go from negative to positive. So it's really, that was the only one. And the endpoints. So our answer has to come either at 1, at -5, or at +5.
Okay.
We know what the function's value at 1 is. It's 3. So that's our answer unless we can prove that one of the endpoints has a value less than 3. Well, let's look at this point right here. Unfortunately, they're labeling this with the values of the first derivative, not the values of the function.
Oh, okay.
That makes it hard. because we're trying to figure out whether the original function is less than 3 there, and if so, what? Or if the original function is less than 3 there, and if so, what? And then we can compare our 3 values to figure out which one. Notice this is absolute minimum. Let me see whether or not I can draw a reasonable facsimile of this function, which is always a bit of a trick. Given the function, or given the first derivative, to be able to draw the function. But it might be enlightening and useful here to answer this last question. I'm going to put the exact same grid, y-axis, Alright, what did we know about this function? We knew it had absolute maximums. Let's see, we know that it's increasing over that whole interval, that there's an inflection point. So it was concave up from -5 to -4. So let's draw it like that. I'm going to try to stay with the same horizontal axis here.
Mm-hmm.
So from -5 to -4, it was concave up. And then at 4 we had an inflection point, and from -4 to -3, it's decreasing, concave down, but still increasing. The original function, this is f of x. In other words, the original function has to still be increasing from -5 to -3 because it's positive. Okay? Then we have a local maximum at -3, and then the function starts let's see, the first derivative becomes negative from -3 to 1. Therefore, the original function has to be decreasing, and there is a inflection point at -1. And so from -3 to 1, we're decreasing. Concavity is negative, so it's concave down to the inflection point at -1. Then it's concave up, but it's still decreasing all the way to 1. Okay. Now we have a flat, but it's still decreasing. Okay. And now from 1 to 2, the first derivative is positive, original function is increasing, and the slope is increasing. First derivative of this is positive, it's got to be concave up. So it's concave up through 2. At 2, it flattens out again. No, hold on. No, it doesn't. First derivative goes, okay, that's an inflection point. So all that means is we go from concave up to concave down. This is concave up. This is going to be concave down until we get to the point 4 where it flattens out again. Slopes go from positive to negative. So something like that is our original curve.
Oh, yeah.
It would appear that the absolute minimum has to be at 1.
What would your justification be?
You think for a moment. As to why it's not at the end points. In other words, could I just as easily drawn these endpoints down there like that, such that they were below that local minimum? Well, they do give us some information about this point, and I have drawn it incorrectly. They do tell us that f of 1 is 3. So the way I've drawn it really needs to be more like that. So let's do that first of all. And now f of 1 is 3. In other words, that point right there is 3. But f of 2, now see these points here you can't use for the original function. I'm going to have to think about this more, Jackson. I'm not positive on how we can prove that this is the absolute minimum and not just a relative minimum. Somehow going to have to prove that this starting point is either above or below 3, and it figures that it's going to have to be above, because I don't think there's any way we're going to put a number on those starting points. And if we can't put a number on it, there's no way I'm going to be able to prove they're below 3.
Okay.
But I'm going to have to think about this a little further. Let's go ahead and end it. And I'm glad you don't have a test on this tomorrow. And I might have to think about this. Get back to you next Friday on it.
Yeah, I can ask her about it too.
Well, yeah. If I have any significant revelations, I will email you or something between now and next Friday.
Okay.
There's a way to do it. I'm just not positive I know how. I may have to do a little research. Okay? But these are always the toughest questions of calculus. Boy, I'm impressed with how tough your class is. It's just a standard AP Calc course, huh?
Mm-hmm.
Which high school do you go to?
Thunder Ridge High School.
Which one?
Thunder Ridge High School.
Thunder Ridge? Okay.
Yeah.
Yeah, I never get the easy questions from you. I always get these questions based on graphs of functions versus first derivatives versus second derivatives. And that might be the hardest part of calculus. So anyway, let me look at this a little bit further, and if I have any great revelations on this particular problem, I'll send you the answer before Monday. If not, I'll just talk to you on Monday about it, and maybe your teacher will have enlightened you by then.
Okay.
Okay? All right, Jackson. Talk to you later.
Thank you.
Have a good weekend. Bye-bye.